Welcome to EDU World Space.
Here we're just going to review what filters buy you when you're doing photometry on stars. But basically, because of blackbody radiation and the fact that there's a peak wavelength at which a certain temperature blackbody radiates a lot of its energy, we can basically use color differences as a measure of temperature. So this is the reason why astronomers typically use 3 filters in order to take photometry on stars. One of the 3 filter triplets is U for ultraviolet, B for blue, and V for visual. So we're going to take a look at some data for our sun. It has an effective temperature equal to 5,777 Kelvin. Now, if these filters were perfect, and the sun did not have a lot of absorption lines, the data for the difference between 2 filters, U minus B plotted versus B minus V, would fall along the ideal blackbody curve shown in blue dashed. But of course, the data point will not fall there. If you go look up the data for our sun, let's just talk about what some of that data means. A big M means absolute magnitude, so remember that that is going 10 parsecs away. BOL, remember that means bolometric. And what that typically signifies is that all the wavelengths of light are being picked up by your measuring device equally, which is not very realistic. So there is something called the bolometric correction, or BC, and this is all data from Appendix G. So this is data that's been carefully worked out and has been agreed upon. The bolometric correction just corrects the visible wavelength for the fact that it's not picking up all the wavelengths. And we'll see that in a little bit. But if you had a bolometric correction of 0, that typically means, yeah, all your wavelengths are coming through that visual filter. Not likely. Big M with a subscript on it like V means the magnitude absolute taken through a visible filter. So we can see that basically your magnitude bolometric is equal to MV minus BC, and we'll get to that. And then we have some color information. U minus B is plus 0.195, and B minus V is equal to plus 0.650. I will put that data point on the color diagram, and we will compare it to Sirius to begin with. Okay, so our sun is slightly positive U minus B and a quite positive. I may not put that dot exactly right, but approximately there is the sun. And we're going to compare it to the very bright star Sirius, which has a U minus B of minus 0.04 and a B minus V equal to 0.01. And the thing to note is that for our sun, B minus V is higher than the U minus B, and likewise for Sirius, but the difference is quite different for the two. Sirius winds up to be very close to 0. I'll try to put it right on top of 0, 0. And you see that the two stars are kind of following the black body curve. Which is basically going towards hotter stars up and to the left. So we can definitely see from the color filters that the sun is cooler than Sirius. And that's really the point of these color diagrams. It turns out that the type of star you have also, whether it's a supergiant, main sequence, etc., also follows a pattern on a color diagram, which you will get to when you do the HR diagram. But anyway, let's take a look at some filter relationships. What do you do with the bolometric correction? The bolometric correction just corrects for the visible wavelengths, and you can use it for both absolute magnitude and apparent magnitude, as long as we're talking about the visual quantities there. And remember that apparent means seen from Earth, whereas absolute means seen from 10 parsecs away. We've already seen that the bolometric correction works for the sun with the absolute magnitudes. Yeah. And now let's use it with our apparent magnitudes and figure out the apparent visual magnitude of the sun as it would appear from Earth. The bolometric apparent magnitude is minus 26.83 for the sun. And we are not going to have very much difference there. So solving for that, the apparent visual magnitude, which means the apparent magnitude of the sun seen from Earth, minus 26.75. Yep, not much different. Okay, but once we have MV, we can actually find individual filter magnitudes if we wanted. So for example, remember, okay, so I'll write some things down, but B minus V is equal to magnitude seen through the blue filter minus the magnitude seen through the visual filter. And those are apparent magnitudes on the right, B minus V, and the absolute magnitudes as seen on the left. Okay, so we have V, that is basically minus 26.75. So B plus 26.75 has to equal B minus V plus 0.650. And we can actually solve for the B. It is minus 26.10. And then we can even solve for the absolute magnitude in the blue filter. not quite right. What is the magnitude of the sun? Is 4.82. Yes. With a minus sign in front. Yes, let's see, we're getting this mixed up. So in the blue filter, we have 5.47. And so remember what the difference is. The B is apparent, B magnitude through the blue filter, and M sub B is the absolute B that you would measure if you could put the sun 10 parsecs away. Okay, and of course that's going to be much lower. And we can do something similar with U minus B. U minus B is equal to, from the table, it is 0.195. And that is equal to a couple things. But we will start with magnitude of U absolute minus magnitude of B absolute. And you can see sort of the bootstrapping. You find an unknown through one filter, and you move from there. And actually, we're kind of working backwards because you would typically do the measurements through the filters and work out the absolute magnitudes from there. Okay, so the B is minus 26.10, and that difference is 0.195. And so this gives us U is equal to 0.195 minus 26.10. So U is minus 25.91. Yeah, and kind of going back through, what we can see is that and it doesn't matter whether you're thinking of apparent or absolute, but the pattern is that the visual magnitude of the sun is basically, let's see where V is. Yeah. M sub V, yeah, let's just circle M sub V minus 26.75. Let's take a look at the apparent magnitudes. The visual magnitude is more negative in the visible region than it is in the blue, which is more negative than it is in the ultraviolet. And what that basically says is that the energy at which our sun is emitting is more shifted towards the visible portion of the spectrum than it is through to the shorter wavelengths. And that is really the idea of temperature, that as more of the energy gets shifted towards blue and ultraviolet, you have a hotter star. But again, we can see temperature for where our sun falls on the color diagram. It is shifted more towards the right. and therefore more towards lower temperatures than Sirius.